Welcome to the session just after lunch. I think people will be trickling in here because some of them got to lunch late, but hopefully we'll see a stream of people coming in soon. So this is the session on free inference and instant training, breakthroughs and implications, and we have a stellar set of speakers here today. Mathai and I are chairing the session. We're just going to, set the stage, introduce the speakers, and hear from them. So, in this session, our aim is to take the blinders off and fire the imagination of the systems and machine learning community. Much of the community has focused on sort of speeding up training, making it more efficient, making inference as cheap as possible. And most of the work has focused on deep neural networks. We want to ask the question, if all these problems were solved, what should we be looking at next? So we want to do this at various levels, the algorithmic level, hardware level, what new hardware should we be considering, and sort of frameworks and applications. What are the new applications that we should be considering, and not just, the standard image classification or translation applications that have been driving this field for the past couple of years. And so in this context, we have 4 speakers here today. If you want to look at the universities, they represent CMU, MIT, Berkeley, and Stanford, and MSR too, recently. So, 5 organizations among 4 speakers. More importantly, they're all experts in ML theory and algorithms, systems, hardware, and applications. And so we are very, very grateful that they're here today to share their thoughts with us. I'll let Mathai introduce our first speaker to kick us off.
So our first speaker is Michael Jordan, who's the Pihong Chen Distinguished Professor in the Department of Electrical Engineering and Computer Science and the Department of Statistics at the University of California at Berkeley. Professor Jordan is one of the leading forces in the machine learning community. It's a broad statement, but it's actually true across many different areas of machine learning. He's known for his pivotal work in a broad set of areas, bridging computational, statistical, cognitive, and biological sciences. In particular, his work has been kind of central in sort of understanding the statistical foundations of machine learning, in addition to developing algorithms and a lot more downstream work. So without further ado, here's Professor Michael Jordan.
Okay, hi. Did you get my mic on now? Okay. So I gather this is a systems-focused crowd, so I will have that in mind. My overall message is going to be that machine learning is in great growth mode right now. It's not one thing. It's a whole bunch of different kinds of related challenges. And so think about not trying to build a single database or Unix or something, like one tool that solves all problems in the field. This is really more like tools. And so think about someone who builds houses. They have a screwdriver, and they have a hammer, and they have a saw, and all that. And that hadn't changed over centuries. And it's not going to change. So there's not going to be one tool. This is a bunch of tools. So I have a lot of respect for systems people, and I really want to continue the partnership, which is emerging. In fact, when I first went to Berkeley, I was coming in as a machine learning person. This is 1998. And they said, well, that means you're in the AI group. I said, no, I know nothing about AI, and I don't really care. I don't want to build artificial humans. That's not interesting to me. What I want to partner with is the systems people, because they got a perspective that I think I really respect, and I want to learn more about it, and I think there's where the power is going to be. And they continue to want to label me AI over the years, and I've never worked on vision or robotics, and I don't really care. I shouldn't say this on a video, but I really care about engineering systems that really change the world, really large scale, move data around and all that. And if it has vision or movement in it, that's fine, but it's not my main focus. All right, so in fact, my perspective on what's happened in the last, say, 23 years is a bit different from the story you usually hear, that it's all about neural nets and computer vision. So I think, first of all, 20 years ago, it was about the back end. Fraud detection was really, really important in the history of machine learning. It really worked, and it really changed the business model for Amazon and a lot of other, and the banks. We wouldn't have Amazon today if they hadn't been able to solve it with random forests, actually, early classification systems. Supply chain management. How do you have an Amazon if you can't get all the pieces together to build all the parts for a billion products to serve hundreds of millions of people, right? Well, you model all of that with machine learning, and that was done back then. So after all those systems had been built, and this was partly systems building, they had random forests really built as really good systems. People started to think, well, can we turn that onto the front end? Can we have humans, their data in the loop? Can we build recommendation systems and so on and so forth? So I think that was what happened next. And I think what we're in right now is really what I would call end-to-end. You know, it's not that there's been a revolution in the technology, and yes, there's a lot of data and all that, so in some domains that's kind of impressive. But it's not that different. What it really is that we have some end-to-end capabilities now. So you can build almost as a commodity a speech recognition system. And it's an end-to-end system. It takes in the waveform and outputs, you know, something like text. It doesn't solve the problem, but it's a useful commodity for all kinds of other things, and similarly with vision problems and so on and so forth. So end-to-end is both good and bad. It allows you to build a whole commodity. On the other hand, it couples everything together in a really complicated way, and it makes it hard to actually build systems around those kind of capabilities. So I don't think it's the model going forward. So I think what's missing right now is actually what we're seeing emerging is the kind of economic perspective of you make intelligent systems by having lots of kind of dumb local decisions in a market with bidding and pricing and all that, and out of that starts to emerge intelligence. So first of all, I don't like the word intelligence. I've said this in lots of talks, but because we don't have it, we don't understand it, and we're not really building it into our agents and all that. They're not intelligent. They're taking in data and mimicking what they see in the data, right? And if we're ever going to get intelligence, it's going to have some economic principles, because that's, you know, a system that brings all the food into San Francisco every day, to have every person in every restaurant have all the food they need at the right place at the right time. That's an amazingly intelligent system. But as you know, there's no intelligence at any point in that system. Everybody's just thinking about, should I bring another head of lettuce into a particular, you know, street address? Okay, so that's for me what's happening. Now I wrote an op-ed recently, and this kind of talk is inspired by that op-ed. If you haven't read that, I would love to have you read it. I do think that it's important to start to use this word AI in a more sensible way. It's being used as an intellectual wild card, in my view. Whenever anybody doesn't understand what they're really talking about, they say AI. And I should say, I think Mark Zuckerberg has done that better than anybody, sitting in front of Congress saying AI whenever he didn't know what else to say. And I think we need to move beyond the usage of the phrase in that way. All right, so it was originally McCarthy and these others who had this human imitating perspective. Would it be interesting, fun, challenging to make a computer act like a human? So let's try to imitate the human. I don't think that's what's actually happened over the last 50 years. I don't think we've done that. I don't think we can imitate humans at all. But what's really happened is we've built IA systems. We've built systems that augment human intelligence. Search engines, intelligent translation, translation and so on, augment human intelligence. That will continue, and it uses data, and it uses actions, and it uses models and neural nets or whatever you want to do that. But I think the bigger picture, which we're seeing emerging, is what I've been calling II. Again, none of this is invented by me, just kind of trying to put a highlight on it. It's Internet of Things meets data analysis and statistics and decision making. So not just taking in data and crunching it, but making large numbers of federated decisions in a context of large numbers of agents. Hundreds of thousands of agents simultaneously doing things. That's what we're seeing emerging. And that's not the classical AI perspective. You have one agent making a decision with all the data it has and maybe making a sequence at best. And the real world is 100,000 agents making a bunch of correlated decisions, which can be good or bad, like the financial system or the medical system or the transportation or so. That's the world we should be having more intelligence in, and we're not really thinking enough about that. Okay, so let me just actually skip this slide. I'm just sort of saying about, I don't think with human imitating, we're not as far along as everyone seems to think. Even in vision, you know, the systems work pretty well with pictures on the internet. They don't work well when you go out in the real world. You can train them up with huge amounts of labels and huge amounts of effort, and so like, you know, Tesla's doing that to build self-driving cars, and that's fine. You can probably do something in that particular niche, but we don't have systems that really understand the visual world the way we understand the verbs and the nouns in the world, not just you know, picking out a few things in images. And so it's a great field, computer vision, and it's not over. It's going to be decades before we start to get somewhere with it. So we're not there yet, and that's great. But here's the main point, or it's one of my main points, is that I don't think human imitating AI is the right goal. It should be to build really large-scale systems that take in data and make all kinds of decisions at all kinds of scales, maybe for people, maybe for not, but it's that kind of system that we're trying to build. And I do think about domains, not like vision or robotics, but I think about medical domains where you're taking in all kinds of data all around the world right this moment, and decisions are being made for people's health right this moment, and all those things should be related. so that if you discover something good for Jeff and Jeff similar to me, that should immediately apply to me. And if we start to make errors, we should control those so we don't make too many errors, and we worry about provenance of how the data was collected in this particular situation. Is it still relevant for this situation? All the kind of things you think about, like in the banking industry, about how you move money around, think about doing that for things like medical decisions. So think about all the systems issues there. So that's not real AI, but it's really, really important. All right, so just this kind of phrase I like to say: to make an overall system behave intelligently, it's neither necessary nor sufficient to make each component of the system be intelligent. So if you've ever did statistical physics or economics, this is very familiar to you, but it's not enough expressed in our field. Okay, we want to think about systems that are really intelligent because they maybe have market principles. Here's another kind of provocative point, which is that if you ask people what they're working on who are doing the current AI wave, they often will say, oh, intelligence. We're trying to understand intelligence. Again, I personally don't think that's what we're doing right now. If you work on natural language semantics, you're starting to get there. It's not that no one's working on it, but most people aren't. Just taking in data and doing neural nets is not intelligence. But the other thing they often emphasize is autonomy. All right? I'm going to build an autonomous system, because as if that's, so why? Well, if I can build an autonomous system, I can sit back and say, wow, look at that, I did it. It's intelligent and it's autonomous. It's a bragging point that I was able to, I don't have to guide it. And if you're a roboticist, that's a reasonable goal. But for the rest of us, I don't think it is at all. We want to build a system that integrates well with the rest of us, right? And it shouldn't be autonomous. Even a self-driving car shouldn't be autonomous. It should be communicating at all times with all the other cars around it. And if a tree fell down, it should tell all the other cars. And it should be highly networked, and all the incentives should be set up so that it goes down the right street at the right place, depending on all the other traffic, and so on and so forth. It should not be autonomous. It should be exactly the opposite. Okay, so I'd like to demote autonomy as the goal. I think it was like a bragging point that we build autonomous systems. We should brag that we're building highly interconnected systems. All right, so here's my favorite slide for this particular talk. These are some of the things I really work on and have been working on for 10 or 20 years. I consider these challenges in the broader enterprise of intelligent data-oriented decision-making systems. Let's call this II. If you look at those, most of those are not the classical AI goals. Okay, some of them are, like abstraction and explanation. But a lot of them are not. So multiple decisions, I don't mean just a sequence. I mean like 100,000 related decisions at any given moment. How do you do that? I'll talk a little bit about that. Systems that create markets, that don't just create a so-called intelligence. Dealing with uncertainty, still to this day, things like neural nets take in an input, they produce an output, and there's no uncertainty associated with that. That's just dead wrong for the future. If you're going to make medical decisions for people, and you make an output that says you have to have a heart transplant, I want to know how sure are you of that? Did you look at this other data? Do you know this thing about me? Let's have a dialogue, and that's part of the explanation. What if experiments, all that has got to be surrounding these systems. So how do you do uncertainty? Well, things like jackknife and bootstrap, you resample, you try out alternatives, you look at what if experiments. That's how you assess uncertainty. And our current systems, I mean, there are algorithms for doing this, but our current systems don't do any of that, okay, mostly. There are Bayes nets that kind of put in uncertainty with a prior probability, but there's very little frequentist uncertainty. Cloud edge and interactions, if you're systems people, you know the importance of that. We'll have different knowledge in different places when we have cloud and edge interacting at different timescales. And you got to be thinking about that. How do you coordinate all the different out-of-date knowledge? Abstractions, I just emphasize that. If you were to ask me why do you not think we have intelligence right now, that's the main reason. Humans are extremely good at thinking up and thinking through abstractions. That's what we do in computer science really well, but that's what we do in mathematics, that's what we do in science, that's what children do extremely well. And that's what our current systems are just incapable of doing, right? I mean, yes, you have a little bit of features in neural nets that do vision, and that's being called abstraction, but that's far from what that's what a really intelligent system can do, is think up and reason with abstractions. So it's a research problem. Doesn't mean we shouldn't work, that it's a research problem. It'll take a long time. So let me just dig into a couple of these. Again, I think all of these are, it's not that no one's working on this, not just my group, but many groups are. But when you say AI machine learning, no one has all these in mind. They just have mini batch and distributed training of neural nets and all that. That's what AI is nowadays. And I want people to spread their wings to many of these other really, really important challenges. If you go into a company like this one, or Alibaba in China or whatever, this is the kind of things they actually work on. Most of them don't work on a big system with, and mini batch training and so on and so forth. All right, so let me just mention multiple decisions. In real problems, like transportation, to take an example, you can't just have each entity be autonomous and thinking about nobody but him or herself. You have to make a lot of link decisions. These decisions will often interact. Now, if there's no scarcity, they don't really interact that much. But as soon as you have scarcity, like in a real-world economic system, then decisions will start to interact, and you have to worry about that. Okay? So let's think about systems that create markets. Now, let me take just a very, very simple example to try to bring this home. Recommendation systems, to me, were one of the more powerful achievements in machine learning literature, or machine learning history. Okay? Before the current era, they took in lots of data and they helped people make decisions, not just find features and so on. They help people make decisions. What books am I interested in, and so on. The way they work still to this day is that none of the decisions interact. So if I come in to the Amazon system today, they'll featureize me in some way. And they'll put me probably into a neural net these days, and they'll output some recommendations. There's some books or some movies or something else. Chris comes in later, they will featureize Chris, and they will put him into the same neural net, and they'll make some recommendations for him, and those are totally unrelated. Right? Well, so if you're recommending a movie, that's fine. If they recommend the same movie to me and to Chris and to all of the rest of you in the room or to hundreds of thousands of people, that's no problem. They just stream the bits to everybody, no problem. What if you recommend the same book to everybody? Well, it's probably still not a problem. You can do what's called print on demand, but getting maybe 100,000 copies of a book to all the people who ordered it today, that's not easy. So it starts to become a little scarcity there. But now, what if you recommend, you're trying to make a really good recommendation for things like restaurant seats that, not just a bunch of advertisements, but actually really bids and, link you up to restaurants that you might be interested in and maybe get 10% discounts and so on. Well, you can't recommend the same restaurant seat to 100,000 people, right? And you'll create congestion. So you have to instead build you have to do load balancing. You have to do this really with a market. You don't know what people really want, what their preferences are. You don't know what the restaurants really have available. So you can't just have the computer know all of this. So you have to build a market where the restaurants can bid on the people and the people can accept or reject and start to create a two-sided market. What if I build a really good app for doing how do you get to the airport, pathfinding? If just a small number of people are using it, no problem. But if everybody's using it, it might recommend the same path to everybody, and I create congestion. And that's already you start to see that happening with some of the apps that when they get big. Well, you can't you have to think about that. We can't start creating congestion in our lives. And here's another example. Is my favorite one is that like in China right now, everybody's got a little bit of money and $1,000, and they want to invest it for the first time in their life to have that might buy a mutual fund or something. Well, then now their apps exist which help people to make their investment. Right? Well, if that app suggests to 100,000 people today to buy Microsoft stock, the stock's going to go up artificially, and that's going to move the market, and it's going to destabilize the market. You cannot do that. Okay? All right. So I hope you get the sense this is real. Right? And at the same time, there's the classical problem of multiple decisions that's more statistical. And these are quite orthogonal, but you have to solve both of them. And I hope you all kind of know about how you make decisions now under uncertainty, not under scarcity. If you make decisions under uncertainty, what you do is that you need to make a decision here, do jelly beans cause acne? Well, you randomly put half of your people in, you do an A/B test. Half the people go here, they eat jelly beans, half the people don't eat jelly beans, and then you ask, say, their skin condition 6 months later, and probably there'll be no effect. It'll be within the error bars. And you can get a p-value, a quantitative assessment that you're making a real decision based on uncertainty in this statistical paradigm. But yeah, as you know, the people don't stop there. They don't just make one test. They say, well, it's just a particular color that causes it. So now they do the A/B test, 100 times. All right, and now by chance alone, they put people just happen to have bad skin condition in the treatment condition, and they will look like they have bad skin condition after the test, and it looks like, oh, I've made a discovery. Green jelly beans cause acne, right? Now this is, if you had any statistics, you know about this, but you probably don't know the solutions to this, okay? And the software, I know of no software that anybody has built in the machine learning literature that puts in false discovery rate control, which is one of the ways to deal with this. All right? So you can deal with this. There's a notion called false discovery rate, and it's not an error rate. Error rate is just a single number. All right? It's a ratio. There's a numerator and a denominator, and you want that ratio to be small. You can make it be small by having the numerator small. That's a classical error rate going down, or the denominator can be big. Okay? And so you can control the fraction of bad decisions in your entire lifetime, not just on one day, not just in one decision, or a whole group of people that you can have that fraction be controlled. Okay, so this is something we've worked on at Berkeley. Here's a very recent paper. There's an algorithm called Dagger, and there is the algorithm. You can put that in your software that will control false discovery rate in an online setting across lots and lots of decisions. by making the numerator and the denominator be controlled. And it doesn't require independence and so on and so forth. So this is real, you can do real math with this kind of thing, and it should be done. Put that together with the economic perspective, and now there's wonderful research challenges going forward. Okay. Right. I haven't seen a sign telling me how much time I have left, so I'm a little uncalibrated here. 5 minutes? Okay. Let me say a little bit more about this markets business. So, you know, people talk a lot about AI killing jobs and all that, and there's certainly some truth to that. But people aren't talking enough about ways you can create jobs. And I think that if you take a markets perspective instead of a classical AI perspective, you can start to see this much more clearly. All right? So, consider the music situation. So let's not even call it a market. More people are now making music than ever before in history because, you know, laptops allow you to make really good music. And some people are really good at it. On the weekend, they create great music. They put it on SoundCloud. Right? And then they lose control of it entirely. So then services like Spotify or Pandora will stream it to large numbers of people. And more people are listening to that stuff than ever before in history. It's not everyone listening to Beyonce. They're all listening to this stuff. But there's no market. There's no connection between the producer and the consumer. And so economic value is being lost. Probably billions of dollars of economic value is being lost. Right? So how do you restore that? Well, you use machine learning and economics together to create a market. Right? How do you do that? Well, there's a company called United Masters. Some very famous musicians are behind this, and real tech people. And so they partner with sites like this, and they've looked at the data flow, and they said, well, if there was a data flow, I can put a price on that and make an economic transaction out of it. So I can create a dashboard for musicians. So you know, if Chris, let me pick on Chris again, is making music on the weekend and he drives a taxi during the week, if he has the dashboard, he learns that in Austin, Texas, you know, 10,000 people listened to him last week. He's popular there for whatever reason. He knows he could go to Austin, book a room, and make, you know, $10,000. And if he does that 5 times during the year, that's a salary. So he doesn't have to drive his taxi or be a professor during the week. He can actually now become a musician. And this starts to scale. You can think of now hundreds of thousands or millions of people in various countries actually starting to get a job because they have access to the data about their skill set. And now it doesn't have to be just music. It can be writing, it can be art, it can be all kind of, you know, hair cutting, and so on and so forth. All right, so let's liberate ourselves to think about AI in this way, that we create connections where data flows and we allow economic value to be created, not that we try to replace human intelligence with computers. Last little point in my last 2 minutes, this is just a little advertisement, is that when you start thinking about multiple decisions, you do have to think about sequences going forward, not just simultaneous, which I've emphasized. And this is the area of optimal control theory. It's now often called reinforcement learning, but it's just optimal control theory. And I really want to hope the systems community will start to resonate to the need to build systems that allow you to do optimal control. And so now you have to face the fact that lots of the tasks that you need to run have very, very different lifetimes. That you're going to do a search process through a sequence of control actions, and sometimes you'll learn very quickly that was a bad idea. Another particular path through the tree of actions looks like a very good idea for a long, long time. So if you start synchronous processes up and you have them all wait for each other, you're going to be waiting way too long in many, many situations. So the MapReduce paradigm is not appropriate for lots of these kinds of control tasks. So let me just sort of skip ahead. Here's just a kind of a little picture to suggest this. If you're trying to make a simulated robot perform, then what you're going to do is try all the actions of all the joints and everything and try to build a policy doing that. You're going to do lots of what are called rollouts. And AlphaGo did rollouts. Most of the so-called success reinforcement are all based on these rollouts in a big, big, big tree. All right, so we have been working on this system called Ray. There's several students, and then John Stoic and myself at Berkeley are leading this. And it is all about trying to do parallel version of Python where you can have very heterogeneous tasks. Some of them are very short, some are very long, and there's no synchrony anywhere. It's all a big data flow graph where the graph itself is dynamic. Okay? So I like to think about this as in Python, you've got functions and you've got objects, and they're both really, really useful. When people went to MapReduce, Jeff Dean and others, they kept functions, but they threw out objects. It was all functional programming. Right, so we want to restore objects because we think they're really, really important. So Ray basically does that. So functions are now called tasks. They're distributed functions. And objects are now called actors in the classical language of actors. So they are stateful. So we built a system that does this. Here's some performance. I guess here 60 nodes, we're able to get up to 1 million tasks per second. So tasks are lightweight and they can be used for these rollouts. It is a working system. I'll show you a GitHub address here in a second. Much work on scheduling, local and global scheduling, and much work on making sure that objects are in the right place at the right time. Here's a little bit of code using this. It's basically Python with some annotators, decorators that tell you that some things are going to be parallelized. And I'm not going to show you a little video of this actually working, but I could. Let me just go back to the last slide. So there it is on the GitHub address. And by the way, I'm going to China a lot these days, and one of my big achievements in China is to get some of the companies there to do open source development. And so there's companies doing open source development of Ray for the first time ever in history. So I'm hoping that it'll partly take off in China. All right, so to summarize my message, it's a great era. Don't just focus on neural nets. There's all kinds of other problems, and build systems that focus on all those other problems, because they will be the ones that are actually start to get used in industry and have an impact on the world, and will start to open up new research venues. It's going to take decades to get this field right. This field is really not AI. This field is really a new engineering discipline. It's like my father, who did chemical engineering in the 40s. That was the thing to do in the 40s. Take the chemical principles and turn it into systems, factories. And that's what we're doing right now. We're taking the principles of decision making and data and analysis and all that, and together computing, and we're building systems that make human life better. And that's going to take decades, and I think that's the enterprise we're involved in. So let me just put that slide up again. This summarizes what I think of some of the challenges, but new ones are going to be emerging. So thank you.
Thank you, Professor Jordan. So our next speaker is Chris Ray. Chris is an associate professor at the Department of Computer Science at Stanford. And he's also affiliated with the Statistical Machine Learning Group, Pervasive Parallelism Lab, and the Stanford AI Lab. Chris's research is unique. It sits at this intersection of database theory, systems, and machine learning. Work from his group has been incorporated into major scientific and humanitarian efforts, including IceCube neutrino detector, paleo deep drive, and mimics in the fight against human trafficking and into commercial products. He co-founded a company that was acquired by Apple in 2017. And I guess Professor Jordan's put you on the spot, and you'll be showing us your musical talents too.
Yeah, I don't have any musical talents, Mike, so I appreciate that. Yeah, so what I'm going to talk about today is really pretty much in line with what Mike was talking about earlier, which is this drive to take machine learning and make it into an engineering discipline. And one of the catchwords for this that's going on right now is this software 2.0. Now, the first time I said software 2.0, I have to admit, I kind of threw up in my mouth a little bit. I've soaked up about as much Silicon Valley as one human being can soak up. But even by my standards, that seemed like a little bit out over my skis. But what I started to realize as I walked around to all the different companies and folks that are down there and up here in Seattle is that the way people are building software is really changing, and that's, to me, going to drive a lot of the change for where machine learning research, I think, can have the most impact, and also build the most interesting products to impact the world. So if you've seen these software 2.0 things, the term was coined by Andre Karpathy in a blog post. But when you think about that, you probably think about these really fancy applications like translation, robotics, all kinds of imaging, and you probably think about neural nets, and you wouldn't be too wrong. One of the things that kicked this off is this, Google system that shrank their language translation system from, 500,000 lines of kind of conventional C++ code down to 500 lines or so of kind of, commodity machine learning code. And that same 500 lines of code, more or less, actually, Facebook could replicate, and Microsoft could replicate, and a graduate student in Germany could replicate. And something pretty exciting that these, as Mike was calling them, end-to-end applications are becoming these insane commodities so quickly is really exciting. And it changes where you're going to put the high-value PhD people actually doing any work. But what's been really exciting is it's not just those end-to-end AI first, ML first applications. There's a bunch of stuff that's going on that's really exciting that's taking these principles and applying them all over the place. I'll talk a little bit about HoloClean that Ihab, Ilyas, and Theo are doing on taking these ideas and applying them to problems like data cleaning and the extract, transform, load process and data integration. Andy Pavlo is doing a bunch of really cool work on tuning databases and tuning systems using machine learning. And there's also cool work going on in networks as well. And so this transition where machine learning sort of works well enough that it becomes a building block for these systems means we kind of have to think through how is software engineering going to change. And that's why I think this software 2.0 is kind of an interesting paradigm. So what does it look like? Well, it's a vague buzzword, so let me try and put a little bit of meat around it. So kind of conventionally, software 1.0, you write code, C++, Python code, and you compile down to an ISA, right? Machine-based instruction, maybe kind of CUDA kind of compiling. What's going on in software 2.0 is two big changes, at the top and at the bottom. At the top, what's changing is the abstraction, right? How you actually build these applications. And what you do is you feed them training data, by and large. So that's the input that you're giving to these systems. Underneath, what's really exciting to me the first time in computing since I've been around in it is that instead of compiling down to instructions, you're compiling down to like a BLAS-like, data flow-like call. And so the hardware has a chance to reach up and actually change as well. So both the top and the bottom of software are changing. That seems pretty exciting and interesting. Okay? So why is this happening? Now, conventionally, people focus a lot on quality. They say, oh, I built a system that has higher than human accuracy at text X, Y, or Z under some very, very simple reasoning. But what's exciting is that actually this is a way to build a lot of products with high quality faster. You have people who don't have machine learning PhDs, who maybe have sort of basics of statistics, being able to build and deploy high quality products in a small amount of time. And the speed to develop them is amazing. Also, the maintainability. Rather than having hand-tuned, crazy, featureized systems, they're building these systems that are basically getting all those low-level details right for them so they can focus on building products. So that speed of execution is just dramatically different. What's also exciting is that the deployment story has changed. So neural nets have kind of become, weirdly enough, like a new JVM. And what I mean by that is that they're the language that you compile down when you want to ship code. So the hyperscalers, Microsoft very famously has a bunch of great stuff like Brainwave. You can compile down to hardware for neural nets, and once you do, a bunch of problems are almost solved for you. In particular, qualification. This process you go through at any of the hyperscalers where you have code, you want to ship it to the data center, gets much, much easier if you've compiled down to a neural net. There's no allocation on the critical path. It's using a set of operators that people have pre-qualified. It's changing, in that incentive changes what engineers want to build because they can get their software out there so much faster. Now, in a parallel life with Kunle, the father of multicore, and a guy named Rodrigo Liang, who led a 1,000-person chip group at Oracle, we are actually, some of our research is being commercialized to actually build hardware for ML, which is really exciting. And there are all kinds of underneath changes about how sort of today's neural nets are trained that are allowing sort of hardware to really, really radically change and come up and meet this abstraction. But that's not what I'm going to talk about. I'm going to focus more on that level of abstraction about how programming and building these things is really exciting. So the way we got into this was about 2 years ago. We kind of looked at this landscape of every week, if you remember, in sort of 2016, you would wake up and look at archive and something else would be posted. This neural net does that, this neural net does that. It was kind of a mad dash for innovation. And we looked at that and we said, well, this, a lot of people are working on that problem. We want to work on something else. And we kind of bet that was going to become a commodity. And so what we thought was going to happen, we didn't know the term software 2.0, but we kind of thought that deep learning would basically plateau and hit a commodity point where people could download and build software with it pretty reliably. And so we published this paper in NIPS 2016 that we called data programming that started to think about what was happening up the stack. And I'll tell you about the software that we've been building to implement this idea over the last couple of years. Now, the key observation was that if you looked where engineers were spending their time, they weren't spending their time building new models. They weren't spending their time actually tweaking the underlying systems. They actually weren't even worried that much about runtime. They just put it on some GPUs, maybe they go get a coffee. Where they were spending all of their time was basically creating and feeding training data to these systems. And we thought, because we have sort of a theoretical bent, why isn't there any mathematical structure around sort of creating training data? Why does sort of machine learning conventionally start with data coming from God herself and showing up in XY pairs, even though all those XY pairs were generated by a huge system that's consuming all of people's time? And so what we decided to do was try and build both mathematical and systems models of what was going on there with the hope of both better understanding it and also hopefully accelerating that process. And that's where this thing Snorkel was born. Okay? Now, very quickly, we stumbled on one little technical nugget, but there are many things in this space, and I'll try and highlight them. Was this key idea that if you're going to program software 2.0 by getting training data, then maybe what was holding you back in some situations was leveraging all the sources that were available to you of various different quality. And so what we started to do were develop program abstractions, really simple program abstractions, that could just talk about different sources that were informing your training data. And the mathematical questions were to be able to learn the accuracy of those sources and the correlations among those sources, but without any conventional training data. Okay? Now, when we started this, people were kind of skeptical, saying like, well, we'll build bigger neural nets and that will be the way to higher quality on state-of-the-art tasks. And we didn't care. We said, well, we were going to go after people who were just deploying these things inside companies. who were medical people and all the rest, who just needed to build these products. But what's been interesting is over the last year, the state of the art for things like ImageNet, even a kind of straight ahead benchmark, have both come out of tools that basically allowed you to do more weak supervision on top. Facebook published this thing about using hashtags in various different ways. The AutoAugment people did something really cool that followed up on some stuff that we were up to about learning data augmentations and learning composition. And the point is that these other signals to build real products always exist when you go to build a real product, but the benchmarks don't capture them. And so this kind of engineering challenge of bringing in more and more signal seems to actually be catching on, even for the benchmarks. Another thing that I'll highlight here, Ehab's in the audience, you should definitely talk to him, he's the real expert here, but even on things like conventional things like data cleaning, being able to apply these ideas of weak supervision and automatic feature generation gives you tremendous benefit in terms of precision and recall compared to the state of the art. And Ehab is definitely the expert. He's back over there. You should talk to him about HoloClean. They have a big website, and Theo is working on this as well. So the point is, like, this stuff is coming, but we don't really have any engineering abstractions for it. And that's what I'd like to build. Okay? So we started building Snorkel, led by two great folks, one Stephen Bach and another great student, Alex Ratner. He's on the market this year. You'll see his picture many times. Right? There's his picture. So Stephen Bach, who's now doing some stuff at Google related to this, and Alex Ratner really led this project as well. He's on the market. Please hire him. Okay. Now, what do I want you to show you? First thing is, programming is changing. So not only can we de-skill many tasks, that was our original goal, make it easier for more people to use machine learning. We also realized very quickly in our conversations with folks in industry that even the experts, the 7-figure salary folks coming out of grad school, they were having similar kinds of problems. And that even experts were building and stumbling on these problems of training data generation and data augmentation. So we wanted to study those. The second thing is, if you look at classical questions around supervised machine learning, once you start to realize that you don't have labeled data that you can trust, many different things actually change underneath the covers about how you estimate source accuracy and correlations and all the rest. There's a bunch of really classical theoretical work that goes underneath the covers that we're really excited about. And the point is also, there's a lot more to do. All kinds of things in the pipeline, data augmentation, ETL, can be modeled and potentially make it easier to build applications. And I don't claim that we have solutions that are even very good, but they're our first cut on these solutions. And there's a lot more to do to be able to build these end-to-end machine learning kinds of products. Okay? So as I mentioned, this is mainly a trolling slide. Data was the new oil, so training data is the new oil. I have no real idea why. But it's really a fundamental problem in machine learning that you need high-quality training data. As Mike talked about, most of the applications of deep learning, or almost all of them, really come through a lot of supervised data. Okay? And as I mentioned, traditional view is that this data just kind of falls out of the sky and you're given it. But every application that really generates dollars that I'm aware of, that training data was created by a process. People, software, all kinds of things go into that process. And the key idea that I want to show you is that by modeling that process, that provenance, and Mike used the same term as well, modeling the provenance of that process actually can improve the quality. And that's kind of the art project of it. Is it possible that going and understanding that pipeline and mathematically modeling it does anything for the downstream task? And actually the answer is yes, and that's what we've been working on for the last couple of years in this project. Okay? So that's what Snorkel is. It's all online. We've been running workshops about it. As you'll see, there are a bunch of users for it, which is exciting. And we've been modeling this training set creation process and data augmentation process. And there's a blog and all the rest of that crap. All right. So how does it work? I won't go into too much technical detail because we have really short talks, but please ask me, please check out the blog and send feedback. The first and simplest abstraction that we could use was this idea of just functions. So the idea was that what you're going to have is a bunch of maps that took your training set in and then mapped to every point. You can imagine it's binary classification just to make the discussion simpler. Yes, no, or I don't know. I don't know is critically important, by the way. That's where a lot of the interesting intellectual work happens. And you would provide these functions, and they would generate noisy labels. You don't know the accuracy. You don't know the correlations of the labels, but you know that they're probably not of perfect quality. Then the second piece is that you would model those labeling functions outputs. And we chose to model them as graphical models, basically for historical reasons and because we could prove theorems about them. And you would try and figure out in those graphical models, what are the parameters of those models? How accurate is every source? How correlated is it with those different pieces? But the twist is, instead of seeing a bunch of observations, we would only see where they agreed and disagreed. And we would try to come up with basically statistical models that would allow us to conclude we could learn those parameters provably. And And that's basically the program that we've been on for the last couple of years, where you don't actually get to see the value y. Okay? And then finally, to take advantage of all this nice deep learning stuff, we would then label the entire training set with accuracy. So instead of getting a 0, 1, or -1, you'd get a probability distribution. And we would pass that to a deep model. And we would hope that that uncertainty quantification would allow it to do a better job. It would know to trust some points more than other points. Okay? Now, I don't have slides here, but you can definitely look on the website about this. This actually surprisingly has big impacts on things like natural language processing applications, cross-modal applications, all kinds of different places where we've demonstrated this on NLP and vision and images. This quantification of uncertainty actually seems to help in some cases. That it helps ever is great. We're really excited about that. And it never seems to hurt. And that's really the kind of theory that we've been trying to work out. More importantly, it changes how people program. And so we've been basically giving demos to people and allowing them to write code on it. And a bunch of folks at industry and companies, and I'll put some logos up later, are actually using this to build applications. And so what we're after here is trying to understand how this changes the programming model. And again, we're at the early days here. We don't exactly claim that we have the right thing. But there's a lot that can change when you start to view sort of your way of programming as generating training data. Okay? So let me give you one example of something that changes kind of concretely. There's actually a real person who was building one of the early versions of the system using a technique called distant supervision. Okay? So what they were doing is they first wrote a bunch of these, in our terminology, labeling functions. And they were very highly accurate, very precise. They labeled, let's say, 10,000 points at 90% accuracy. Okay? Then they came along and said, you know, I don't have enough coverage in my model. What I need to do is label a bunch more points. And they wrote a lower quality labeling function that labeled, let's say, 1,000,000 points at 60% accuracy. Now, conventionally, what you would do is basically assume that all those labels came from a uniform source. And as a result, what you would have without modeling that lineage or provenance was a set of data that looked like it was about 60.3% accurate. You wouldn't remember, if you like, that you had that high accuracy pool. And unfortunately, that will make your overall model quality go down, which is extremely bad and frustrating as a user of this programming model, because you gave the system more information, and then your quality to the eye looks much, much worse. Very, very frustrating. But of course, as I've told you, kind of the fix is obvious. If you remember where these came from, even if I didn't tell you the accuracies, you would have a better job of estimating which training points you should trust, which were high precision, which were low precision. The art is to figure out automatically what those accuracies are without seeing training data. Okay? So this is a very frustrating experience for user, but it's the kinds of things that we've been basically publishing papers about. And so without going into too much technical detail here, basically we can provably learn the accuracy of these labeling functions, even among correlations among them, without hand-labeled data, and even features under which they work. We can actually surface features of them. And this is a sort of long, we're not at the end of this. We continually keep publishing essentially improvements to when we can learn and can we match supervised scaling rates. In many cases, we can match supervised scaling rates. In some places, we can estimate correlations. We may actually improve some old supervised bounds of learning graphical model structure with this over the summer, which is really exciting. So this is the goal. Change the programming model and figure out what we can offload and make automatic and understand the minimal statistical assumptions that allow us to basically carry out this program. And that's what we've been after. One thing that was just posted, it's been in use with a bunch of our collaborators, is doing multitask supervision stuff and multitask learning. It turns out real applications don't have just one kind of classified output. By learning across multiple tasks, you can do a much better and more robust job of dealing with error. This is something that we've put out, and actually, Mike mentioned Alibaba. These guys are amazing. If you're not paying attention to Alibaba, compared to a US company, they're amazingly open. They took our software when it was like as alpha as possible, used it, showed us where it was used in their pipeline, gave us a bunch of feedback, and actually, in part, some of the reason we prioritized doing the MTL stuff was because of that amazing technical feedback they gave us. Okay? So this is something called Metal. It was just released, and the theory has gotten dramatically cleaned up. It's a little bit more fancy than it was before, but mathematically it's much nicer. And it's practically quite useful because you can build these tasks at multiple different levels of abstraction. You can do parsing, natural tagging for types. You can do question understanding, all in one model. And sort of where one model is weak, another one could be strong. And you can actually characterize this and why it improves generalization. A lot of that was done 10, 15 years ago when people were looking at how multitask learning was actually beneficial. But in this new regime where you don't trust your training data, there are a couple of twists and turns there. But it's a great software abstraction. Okay. As I mentioned, this software is only about 2 years old, but here are some of the users and sponsors, and there are actually many users who are not on the slides. We run these workshops, and people kind of are able to build something with it. Again, this is not great software. This is graduate student stuff, but people are able to pick it up and actually use it because it fulfills this niche that there's no programming abstraction. So our bar is pretty low, because there's nothing else that's allowing you to kind of think about that training set generation process. And I hope some folks get excited in the audience and build something much better than what we have. Okay. I was asked to give a hot take in my last 2 minutes, and so I will. So one of the things, Mike was talking about, the difference between AI and machine learning. I think sometimes even learning itself is not what people actually want in industry, or it's overused in a way that maybe leads them astray. Now, there's nothing wrong with learning. It's fantastic. The generalization results and all the rest are great, but they're sometimes misapplied or misunderstood by engineers, and it leads them into a kind of a morass. So as I mentioned, ML's big impact to me has been how it changes software engineering and deployment. It's introduced this new JVM-like layer, and it's allowed people to program far more easily than they could before. But a lot of what engineers really want is just not to have to tediously specify every line of their program. They really want something that looks a lot more like interpolation. And so we actually started thinking about this a while back about, well, what would an interpolation system look like? Now, conventionally, if you talk to an ML person, which is not formally true for any reason, the inequality goes the wrong direction to make this statement. They think that interpolation implies that you're not learning, because interpolation means you're memorizing the training set. You're getting 0 loss. But these two things are not actually in opposition. You can actually get robust interpolation. You can get everything right. You can do what you're told and still learn and generalize to the rest of the data set. And this is a pretty interesting thing, because traditionally when I watch engineers struggle, they'll say things like the model is overfitting, but they'll have no idea that what they're talking about is the error that's on their test set to their validation set. It has nothing to do with overfitting. But they sort of adopt this ethos that learning basically means you have to make mistakes. And that's not true on a lot of the products. If 100 people ask a question every day, every assistant in the world should get it right. That doesn't actually happen. Okay? So I think reliable interpolation is one way to think about sort of a next generation for where learning and statistical ideas can really play well. Now, when I was thinking about this, I thought it myself it was kind of heresy. But then I went to ISMP, which is this great conference, this mathematical programming conference. And I was lucky enough that Misha was speaking after me. And as a result, I was reading some of his papers. Misha's at Ohio State. You should check out his work. He had this really cool stuff, which is a little bit insider baseball, but it's pretty interesting, which is about how kernel methods can actually interpolate, a family that can interpolate, people knew that part, but could also get mini-max optimal rates. So sort of like the best rates you could hope for these kind of non-parametric estimators, in a corresponding holder class. This is really fascinating, because it means that they're not in opposition. So we have a chance of building dramatically more reliable systems than we were building before, potentially. Right? So that's an interesting way to think about it. And also, those minimax rates are all up to label noise. And so as I was talking about before, kind of the role of why we're modeling label noise in our construction process, you could potentially get better rates by modeling that noise. And that's a program that we're carrying out right now. If you haven't run Misha's stuff, it's amazing. Like, his work is really like, it's one of those fun times of being in academia where you read someone else's papers and send them like frantic, happy emails about how exciting it was. And I got the chance to go hang out with him in Bordeaux. So definitely check his stuff out. I think it's super cool. So that's the end of my talk. Is it the end of the reality distortion bubble? I don't know. But what I wanted to get across to you, if you don't know who the dog is, you haven't been reading enough Reddit. Anyway, but what I wanted to get across to you is that I think programming is really fundamentally changing. It's changing from below in terms of how we actually build our applications, and this opportunity for hardware to race up and meet this new abstraction, where there are a huge number of high-dollar workloads that are going into a fairly narrow but still kind of general pipeline. That's really exciting. I talked a little bit just as proof of concept that, hey, there's more stuff we can model and sort of the process that generates the data for machine learning. That's all Snorkel is really about, and the auto-augment stuff. All that stuff is really about what goes into the top. Can we model more of that instead of having it as a black box? What do those models look like? We showed a first cut, but there's a lot more to do. Thanks so much for your time and attention. Sure.
I forgot to mention that I'm sure all of us have a bunch of questions. We're just going to do a Q&A session in the end with all the 4 speakers up here. So please hold on to your questions. So our next speaker is Vivian C. Vivian is a associate professor at MIT in the electrical engineering and computer science department. She's really one of the world's leading experts in energy-aware signal processing algorithms, and more recently has been looking at ASICs for DNNs and machine learning algorithms. Prior to joining MIT, she was a member of technical staff in the R&D Center at Texas Instruments, where she was a part of the JCT video coding committee in defining the high-efficiency video coding standard. And for this, she received the Primetime Emmy Engineering Award. So she's raising the bar. She's raising the bar really high for these awards, Emmys and Oscars, and Oscar next.
Okay, sounds good. Thank you very much for the introduction. So the focus of my talk will be a little bit different. Primarily, we're going to focus on how do we enable energy-efficient computing at the edge for both deep learnings and beyond that. And this work is in collaboration with a lot of my students as well as other collaborators at MIT. So I'm going to try and cover three key messages in my talk. So first, we're going to talk about the limitations of existing efficient DNN design approaches. Then we're going to talk about looking beyond, we talk a lot about DNN accelerators, but can we get acceleration by looking beyond the accelerator itself? And then looking at other opportunities of doing inference at the edge beyond DNNs in general. So very briefly, what are the limitations of existing DNN approaches? So we know that over the past couple of years, there's been a huge amount of effort to enable energy-efficient processing of deep neural nets, primarily because it's very desirable on the edge devices. And so within my team, we've been spending a lot of time building tutorial material and surveys about this topic. And through this process, we actually found there were several limitations in the existing approaches that I want to highlight for the research community. So the first thing is that because there's been a huge amount of effort both on the algorithm and the hardware side, particularly the algorithm side, we've seen things like network pruning, where you make the network sparse, a lot of different new network architectures to make it more compact, and also reduce precision. In this particular set of work, primarily the focus has always been on reducing the number of max or multiplies and accumulates, so computation as well as weights. But one question that we really have when we're looking at the edge is, does this translate into energy savings? Because that's what really directly matters. And we do know that when we look at the computer architecture itself, or where the energy actually goes, it mostly goes into data movement, primarily through the memory hierarchy. And so really what matters is kind of the order by which the weight or the data that goes to the neural network passes through this memory hierarchy and the data flow of the overall movement. And so in some sense, you can say that the weights and the operations are not all equal. It really matters how they move through the system. To model this, some of the recent research within my group has been to build up a modeling methodology to model data movement. So for example, here this is a model that's based on our Iris accelerator, where you can take in various DNN shapes, as well as the sparsity of the inputs and the weights, and you can get a breakdown in terms of where the energy is actually going from layer to layer, and where in the actual system. And so using information like this, one thing that we first want to figure out is where is the actually energy going. And first thing I want to really highlight is that the number of weights alone is not necessarily a good metric of the energy itself. There's many different types of data movements that go on within the system itself, for many different data types. So for example, if we look at GoogleNet, we know that weights account for maybe 22% of the energy from data movement, but we can see that also feature maps, both input and output, also affect or significantly affect the energy of the system as well through data movement. So we really shouldn't just be focusing on the number of weights in terms of trying to estimate the energy cost. And so one thing that I really want to emphasize or push is that the idea is that what we want to do is, rather than taking weights or number of operations as a metric that we want to reduce, so they're really easy to calculate by looking at the neural network itself, if we really care about energy or latency, we should directly target those particular metrics during the design of the neural network itself. And so we can show, for example, one example of this is the EnergyAware Pruning approach. And the idea here is that if we sort the layers based on the energy consumption, and let's say we start pruning the layers that consume the most energy first, we know that as you prune more, accuracy tends to go down. So you basically want to spend, get the best bang for your buck, spend the money, spend the pruning where it matters the most. And if you do that, as opposed to just removing weights that tend to be small, you actually get better energy savings. So compared to a typical magnitude-based pruning approach, which is actually quite effective, you can do even better with energy-aware pruning by really removing the weights where they actually matter. So we can see here, for example, on AlexNet, about a 1.7x reduction in energy by driving really the algorithm design based with the energy metrics as opposed to just looking at number of weights. One challenge, of course, is that what if you don't actually have an energy model available for you? Can you automate this whole process by actually taking direct metrics from an actual platform itself? So this is some work that we've done recently with Google's mobile vision team, and the idea here for NetAdapt is that rather than again, using an energy model to estimate the energy or the latency, we can take direct measurements from a mobile platform itself, and this will incorporate things like the effects of the tool chain, and if you have some proprietary hardware where you don't actually have the low-level details of, you can still take that information, those metrics that you care about, and insert it into the NetAdapt algorithm and automatically adapt the algorithm to really minimize either latency or energy. Or a combination of both. And these are much more directed towards the metrics that you actually care about when optimizing the system, as opposed to, again, just counting the weights or counting the number of ops. And to just showcase, the impact of this, if you look at the trade-off in terms of, let's say here, accuracy versus latency, so the top left is better. You can see this is NetAdapt applied to MobileNet, and this is actually the smallest version of, a very small version of MobileNet, which is more difficult to prune. What you can see is that you can get up to about 1.7x reduction in latency for around the same accuracy. And this is really because you're driving the algorithm based on latency as opposed to based on reducing the number of operations. So again, the message here is really, can you incorporate the direct metrics that you care about, latency, energy, or whatever your system metrics are, directly into the optimization of the DNN itself, as opposed to other metrics like compute or number of weights. Another thing I just want to highlight, more looking at the hardware side, is that now that we have many of these energy-efficient DNN design approaches from the algorithmic perspective, the one challenge from the hardware perspective, and when you build accelerators, is that there's no guarantee as to which DNN approach or algorithm an algorithm designer will actually use and try and launch onto your hardware. So what's really important also is to be able to develop hardware that's flexible enough to exploit these different features of these DNN algorithms. And so one of the challenges that we see from doing this is, particularly in the design of specialized DNN hardware, and they often rely on certain properties of the DNN to achieve the high energy efficiency. So a very typical specialized DNN hardware will use an array of multiplies and accumulates. And one benefit of doing that is that you can reduce the memory access by amortizing the reads across the MAC array. So for example, in this particular depiction, when I read the weights, I can reuse them across multiple columns of the MAC array. When I read an activation, I can use it across multiple rows of the array. So there's a lot of reuse here, and as we mentioned before, memory access is very expensive. So the more you can reuse, the more you can reduce the energy cost and make the system more energy efficient. However, as we mentioned, a lot of these network architectures are continuing to evolve and change. And so usually the challenge with these particular types of architectures that we saw before was that the reuse and the array utilization really depends on specific properties of the DNN. So for example, the number of channels, the feature map, or batch size. And so as a result, when you build hardware that really relies on certain properties of the DNN, but then the DNNs are varying in terms of their architecture, it's not going to enable your DNNs to be, or your accelerators to be efficient across a wide range of compact DNN architectures. The other thing to also consider is that we often want to scale up the size of these arrays for your accelerators, and so it's going to become less efficient if you pin the utilization on certain dimensions of the DNN and then you scale up the array size. The likelihood is the utilization of your array is going to reduce as well. And so another thing is, of course, we mentioned that pruning and sparsity is an also effective method of potentially reducing the cost of processing these DNNs, but this can be challenging if you're going to use this kind of pinned array structure. So one of the focuses of our next generation Iris is really trying to balance this flexibility and efficiency. What we want is to be able to support a wide range of filter shapes, both large and compact, many different types of layers, both convolutional layers and fully connected layers, but also things, if you start thinking like MobileNet, depth-wise layers are also important to support, and that often tends to be challenging because the number of channels is significantly reduced. You want to be able to support a wide range of sparsity, both dense and sparse, since you often don't have control as the hardware designers to the degree of sparsity of the neural network that's going to be deployed on your device. And then you also want your architecture to be scalable. So for example, if I scale up the number of processing elements, I also want to see that my throughput also scales up and that my energy efficiency is also getting better. And so what's really important is that you're able to find, like, if you have a very small compact neural network, you have the flexibility to find where or what dimension you can reuse as much data as possible. And so by having a more flexible data flow in NOC, and which we'll talk about next for RC2, you're able to get an order of magnitude savings in terms of both speed as well as energy efficiency compared to V1. Just to give you an idea in terms of how we're getting this flexibility in Iris V2, primarily the main focus is to have a much more flexible data flow. In particular, we extend row stationary data flow into row stationary plus. And what this really means is it enables you to do more spatial mapping in all dimensions of the PE array so that you can exploit more data reuse in the multiple different layer shapes. So for example, previously, if you're looking at, let's say, a depth-wise layer, you really have very limited in terms of the number of channels you have, but if you can actually also, with row stationary plus, not only fill up your array based on filter width, but also channel groups, and you can really utilize your array much more fully and then have higher throughput and have higher efficiency. To go along with the more flexible data flow, what you also need is a more flexible NOC or NOC to actually support all these different configurations. In particular, you want to be able to have a NOC that you can deliver multicast when you want to exploit high data reuse. So for example, if you have a very large network like AlexNet where there's a lot of reuse opportunity, you want to have a NOC that can find that reuse and make good use of it. But at the same time, you also want this NOC to be flexible in the case where you have layers that don't have as much reuse. So for example, the fully connected layers or the depth-wise layers in the compact networks. And then in that case, you want your NOC to be able to do unicast and deliver high bandwidth to sustain the throughput. And then, of course, as I mentioned, there's no real control in terms of the degree of sparsity that you have. So you also want to make sure that your hardware or your NOC is flexible enough to support both sparse and dense layers in both the weights and activations for the various different configurations, whether it be convolutional layers or the fully connected layers. So that's basically what you can do from the DNN accelerator point of view. So really, again, the message is to have more flexibility from your hardware and to really drive the design of your neural net algorithms using real metrics such as latency and energy. The one thing, though, is sometimes there's a certain limit in terms of how fast you can actually make your accelerator. So one thing to do is also look beyond the accelerator itself and find other opportunities to accelerate your processing. And so I'll give one example of why it's important to look beyond the DNN accelerator, what opportunities there are, particularly in the space of super resolution. Right? So one important kind of application that super resolution serves for mobile devices is, again, taking low resolution images and making it to high resolution image. This can be very useful if you want to transmit low resolution image because you have very limited bandwidth or because just the sizes of your screens continue to grow. So it's very useful for the viewing experience. However, on a mobile device, of course, again, you have very limited compute. And we know that these days the state-of-the-art super resolution algorithms often are CNN based, and in fact, if you were to run them on very high resolution images, for example, from HD to Ultra HD, the degree of compute for these super resolution algorithms are going to be exceptionally high, and they don't map well very much to these mobile platforms. So the way that we try to address this is to develop a framework that we can use to accelerate the super resolution. We call it FAST. And the main idea is that you basically insert different super resolution algorithms into this framework. You also take in the compressed video, and then you find opportunities to accelerate it, primarily by exploiting an interesting property of the compressed video itself. So typically, if you look from a super resolution point of view at a video, what you actually view it as is a bunch of stacked pixels. However, as a person who previously worked in computer video coding, the way that I typically look at compressed videos is in terms of a more description of the block structure or the structures of the pixels within the videos itself. So the one way where we get really effectively compressed video is to describe the video, figure out the correlations between the pixels within a video itself. Right? So in fact, the compressed video itself is not just a set of pixels, but a lot of information about how different pixels in the video is actually correlated. And so the goal here is that can we use this compressed representation to help accelerate super resolution itself? So in fact, you can. So what you can do is rather than having a bunch of low-res videos and applying super resolution to every single frame of the low-resolution video, what you can actually do is you can apply super resolution on only one of the frames and then use this correlation information, for example, motion vectors, to actually transfer the information from one frame to one of the high-resolution frames to all the other high-resolution frames. And you can generate basically all the other high-resolution frames without having to run super resolution on every single one. So as a result, super resolution is only operating on a subset of these particular frames. This tends to be much more computationally efficient because this transfer is very cheap. It only involves basically some bicubic interpolation. And again, it involves using free information that you already have in the compressed video itself. So if you transfer n frames, you basically get an nx acceleration. So we verified this particular approach on a wide data set, primarily the HEVC development data set of 20 different videos. We were able to show that if you transfer up to 4 frames, there's actually no loss in terms of quality. And if you transfer up to 16 frames, there's about a 0.2 dB drop in PSNR, which is not too bad at all. Typically, for these particular types of applications, it's really important to actually look at the visual quality itself. So shown here in the video are 3 different renditions of the super resolution. So on the left-hand side, you have the original SRCNN algorithm with the highest quality. On the right-hand side, you have the bicubic interpolation. And you can see by looking at the text of the cards that it's much more fuzzier than the SRCNN. However, then you have FAST in the middle, which has the same complexity as the bicubic algorithm on the right-hand side, but you can see that the quality of FAST compared to the left-hand side is also very competitive. So the main idea here is that while we can do a lot of things to really accelerate and make the DNN accelerator more efficient, there are other properties that we can look at beyond the accelerator itself to improve the processing or make the processing more efficient. In this particular case, looking at much more efficient representations of the incoming data that's actually there for free. So one final thing is looking beyond deep neural networks itself. What are some opportunities in terms of what are the types of processing that we care about at the particular edge? So one of the projects that we've been working on within my group, this is in collaboration with Surtesh Karaman and Luca Carlone in the Aero-Astro department, is how to build very low-power processing engines for autonomous drone navigation, particularly nano drones, where you're talking about drones the size of bottle caps or the size of a quarter. So in this particular project, we built a chip we call Navion that primarily does localization and mapping at under around 30 milliwatts. And the real challenge is really fully integrating all of that processing on chip, because when you're talking about such a small drone, you can't have so many external parts or external components. In terms of what this drone actually does, it actually is performing visual inertial odometry. It's basically taking in an image sequence as well as IMU measurements from an inertial accelerometer plus gyroscope, and it's taking these 2 particular inputs in and then trying to determine, one, the location of the drone itself. So shown on the upper right-hand corner, you can see that based on the visual data as well as some IMU data, it's trying to determine itself in the 3D world, as well as mapping the environment itself. So that's one of the key goals for this particular type of processing. And really, an important aspect of this particular processing is to take in, as I mentioned, the vision input as well as the IMU input. And you want to do some kind of optimization of the vision data as well as the estimated states from the IMU data. And typically, this optimization is done in the form of a factor graph to help you infer the location of the drone itself based on this incoming information. And basically, this involves solving a nonlinear least square factor graph optimization. You have factors that are dictated based on the feature tracks that you see from your vision side, as well as any IMU measurements that are coming in. And basically, this is a large graph. You're talking about over 4,000 factors, all where you're trying to put this on a very small drone. And based on these optimizations, you can kind of update what the states are and figure out what the 3D map is. And so very similar to the deep learning space, you can also find opportunities to exploit things like sparsity to reduce the computation. In particular here, we look at the fact that you can exploit sparsity. You get a 5x reduction in memory, which is very important due to the area cost of these particular devices, and about a 7x increase in terms of speed. So what I want to show here is just there are other opportunities other than DNNs itself where acceleration and the co-design of both the algorithm and the hardware can really enable increased energy efficiency. So to summarize, we talked about the various different design considerations for deep learning at the edge. The important thing is to make sure you incorporate direct metrics such as latency or energy into the design of the algorithm itself to improve efficiency. And it's also really important, given the large number of efficient DNN algorithm techniques out there, to have hardware that can really support flexible data flows and NOCs to exploit both the data reuse for energy efficiency as well as to ensure that your array is fully utilized for speed. It's also important to look beyond the deep learning acceleration engine itself for other opportunities to accelerate your algorithms. In particular, you can look at the representation of the data that's actually coming in this case for super resolution. We showed that that was quite effective. And then finally, there are other forms of inference that can actually use to can actually be processed at the edge beyond deep learning. So we showed one example of using graphical models for localization and mapping for nanodrones. That concludes my talks. Thanks.
Thanks, Vivian. So our final speaker for the session is Jeff Garden. Jeff is the research director for the Microsoft Research Montreal Lab, and also a professor of machine learning at Carnegie Mellon University. Jeff is very well known for his work on AI systems that capture long-term thinking, such as reasoning, long-term reasoning, reasoning ahead to solve problems, planning a sequence of actions, and inferring unseen properties from observations. He also has a very unique perspective now as the head of Microsoft's latest AI lab in Montreal.
All right, thank you very much. So, I thought the title of the session was chosen very provocatively, so I did my best to respond to it. So free inference and instant training, I'm not going to be able to achieve either of those, but I wanted to talk a little bit about how to make these things faster without sacrificing quality. So Jeff might not be projecting. Oh, it was projecting a second ago.
Let's see, what number are you on there? You're on number 11, looks like. So there you go.
All right, cool. Thank you. All right, so I'm going to take as given that the right answer, that we know a right answer for inference, and that it's basically Bayes' rule as implemented in graphical models. But this answer is incredibly expensive, and there are a lot of people who have done a lot of great research on making it less painfully expensive. But it's still pretty hard to pay the cost sometimes. But if we can, it's got lots of benefits, among them being that every node and edge in your model has a semantics, probabilistic semantics, which helps you design a model that takes the best advantage of your data, helps you figure out what your model is doing, debug it when something goes wrong. On the other hand, unless you've been living under a rock, there are deep nets, and they are much faster, at least naively, because they work, basically their inference process is a whole bunch of simple matrix operations, fixed, quickly computed nonlinear functions, and the training as well can be very fast. Right, it's basically stochastic gradient descent as opposed to Markov chain Monte Carlo algorithms that are harder to design and may take a while to converge. So not much semantics necessarily in these things, but they're fast and they're very successful. And so the question I'm going to ask in this talk is, can we get the best of both worlds? Right? So can we design deep nets that look more like graphical models or vice versa, and take advantage of both the semantics and the the scaling to big data? And so what we'd like is a model format that's both practical in the sense of a deep net, right? Practical, you can train it quickly on lots of data and get high performance, but we'd also like to import some of the interpretation from Bayes' rule. So I'm going to take as an example inference on a chain graph, right? Just a whole bunch of random variables connected in a line. And so for this chain graph, right, if the standard Bayes net is a hidden Markov model, but if you're a neural network person, forget about hidden Markov models. You're going to use a recurrent neural network, maybe an LSTM or a GRU or something like that. And I want to say that RNNs are basically Bayes nets already, so we're done. The talk's over. well, not really. But what do I mean that there's sort of Bayes nets already, right? So if you're a recurrent neural network processing along a sequence over time, at any given point, you have to have a notion of what the future is going to look like, right? You have to be representing a probability distribution over the future. And that's true no matter what your architecture is, because as long as you're able to predict the next observation, you can then sample from that distribution, feed in your own prediction, and move yourself forward a step and keep doing that until you have a rollout of the future, right? So you're representing implicitly a prediction about the future, which is, that's the point of Bayes' rule, is to give you a representation of that distribution. And the update rule for a recurrent neural network, right? You didn't learn it by Bayes' rule. You learned it by, let's say, backprop through time. But if you learned it so that it performs well, it has to be doing Bayes' rule approximately, right? Otherwise, Bayes' rule is, the right answer, so it has to be doing approximately that. So what we'd like to do is make this implicit representation more explicit in order to maybe gain better performance and behavior of these models. So the first step is that I'm going to suggest making this implicit representation of the future more explicit. So in addition to predicting your immediate next observation the way an RNN would always do, I'm going to suggest that you should also predict statistics of the future. So things like moments of the next few observations, or the count of the number of observations out of the next 10 that are a 1, or things like that. And if we have enough features, right? Just if you keep adding on independent predictions that you have to make, by the time, after some point, you're going to get that your predictions are a one-to-one map from your latent state, right? So your latent state vector of your RNN uniquely determines your predictions, and your predictions, if there are enough of them, uniquely determine the latent state vector. And therefore, they're also a 1-1 map from this probability distribution that we're trying to represent. And so this representation of a bunch of predictions of expected statistics of the future, I'm going to call this a predictive state. A state because it's a 1-1 map from your actual latent state, and predictive because it's a bunch of predictions. So this idea sounds simple, but it turns out to be powerful. So just a little intuition. One example I like to use is a video of a clock with its pendulum swinging back and forth, right? If you wanted to make a predictive state, you could directly predict the next 2 frames of this video, right? And those 2 frames would encode the state of the clock in the sense that they would give you enough to determine the position and velocity of the pendulum, which is the physical state of the system. So that's a visual example for people who like examples in equations. Let's say we have a hidden Markov model. So we have a transition matrix T and an observation matrix O. And we look at the expected next observation given a current state. So that's the observation matrix times the latent state. The but next observation, one time in the future, is O times T times your state. More steps in the future, you keep including more copies of T. And if you stack enough of them, right? If you stack enough of them so that that matrix has full column rank, which you can always do if there's if you don't have excess useless states in your hidden Markov model, if you have enough of that, then that vector of predictions is a predictive state. So just the expected observation over the next few time steps. So you can add this sort of predictive state to a recurrent neural network, and doing so, there's no necessary reason that it has to make things better. It's an inductive bias. It's a statement about the problems we expect to encounter. But empirically, it seems to help prediction accuracy, right? So the graph I have here is from this paper by Venkatraman et al. It's Drew Bagnell's group, where if you use a particular algorithm for generating a recurrent prediction, in this case of an action in a reinforcement learning problem, you get one level of quality. And if you add as well this predictive state notion and train it to optimize that, This is an example of multitask learning. And it makes, this inductive bias makes your performance go up. All right. Oh, but there's a problem, right? It's still a recurrent neural network. When you train it, it's still going to get you probably to a local optimum, right? So I've heard a lot of people claim that neural networks and stochastic gradient have the nice property that all local optima are approximately global. But the one exception, well, there may be more exceptions, but one certain exception to that is recurrent networks. It is very, very possible, in my experience, to get into a very bad local optimum when you're training a recurrent neural network. OK, so what are we going to do to try and fix that? So I'm going to propose that we should try and bootstrap from supervised learning. So empirically, all of the people making these claims that all local optima are global are talking about supervised learning problems, or at least many of them are. And empirically, it's true. There seem to be fewer worries about local optima when you're training a supervised neural network. And theoretically, it's also true. Like, for example, if you have a linear predictor, a recurrent one can have local optima, but a supervised one cannot. All right, and so let's try and borrow that property. So the bootstrap is going to work like this. We're going to predict our future features directly from a fixed window of history instead of recurrently. So that's going to be a supervised learning problem, right? At any given time step, you have a past and the future, and you predict the future from the past. But it's suboptimal because you have a finite window of memory, right? You can't remember anything for longer than the length of that window. So that's step one. Step two, now I've got a bunch of predictions of the future. And I'm going to take my prediction that I made of the future at time t, and I'm going to add that as an input when I predict the future at time t plus 1, right? So I'm going to chain my predictions together. And this allows infinite memory because a given observation will influence my prediction, and that prediction can then influence the next prediction and the next one and the next one. And so this sounds like I'm making things recurrent again, but I want to emphasize that I'm using past predictions, right? I used an earlier version of my model to make some predictions. I'm adding those to my training set, and they're fixed, so I'm not backpropagating through them. So I've gotten rid of recurrence, but I've introduced a new problem, which is that the training distribution changes across iterations, right? If my model changes, then my predictions change, which changes now because my predictions are input at the next time step. I've changed my training distribution. And so I've broken the assumptions of most supervised learning algorithms. And so step 3 is going to be to fix that problem. And we're going to fix that problem using imitation learning. So a quick detour. Inference, you can think of it as a very special Markov decision process, a very special reinforcement learning problem, where the state is the predictions we've made so far. Our action is to make another prediction, tack it onto the end of our list of predictions, and our cost is the sum of the errors we make in the predictions. And so learning to do inference is the same as finding a good policy in this reinforcement learning problem. But the nice thing is that this is not a general reinforcement learning problem. We actually have an expert, if we have training data, that does a pretty good job, that gives us a good policy to start from. And what that expert does is every time the expert is called on to make a new prediction, it copies that prediction from our training set, right? And so that expert is a good policy. And so reinforcement learning, when you start with a good policy, is actually much easier. It's provably impossible in some sense if you don't, and provably possible in a sense if you do. And in particular, we can reduce imitation learning to supervised learning, which was the desideratum from before. We wanted to be able to bootstrap off of supervised learning. So it's going to do that by a framework called approximate policy iteration. This captures a number of different imitation learning algorithms. So for those of you who haven't seen it, exact policy iteration, in your reinforcement learning problem, you look at every single state and action. So you should already see a problem with this, right? Exact policy iteration requires you to loop over all states and actions in your problem. Calculate some statistics of the current policy, how well it performs starting from each state action pair, and some quantities you can compute from those, including the advantage, which is the difference between the quality of a given action at a given state and the quality of the best action at that state. And so we choose then a policy which switches to the best action, the policy which optimizes the advantage, meaning the policy which picks the action which has the smallest difference from the best action, namely the best action at every state. Now, this doesn't work in a real-size problem because you can't iterate over all state action pairs. You can't exactly calculate the advantage function. You have to estimate it somehow. And you can't freely choose a new policy, right? So I just said that my new policy, I separately set its value at every state, but I can't do that. I have to work in some hypothesis class of policies. So instead, we're going to use approximate policy iteration. So to do that, what we're going to do is effectively approximate each of the steps of policy iteration. Instead of exactly computing this advantage, we're going to estimate the advantage function. And instead of exactly computing this new policy, we're going to update our policy within some hypothesis class to improve a criterion. The same criterion we were trying to improve before, which is, I just want to highlight. So what we want is the expected value under the, if we follow the new policy, and we look at the states and actions we see when we're following that new policy, of the advantage that we see of that state action pair. So we want to effectively reduce the number of times we're taking suboptimal actions in a given state and reduce the amount by which they're suboptimal. And so to instantiate this, so this is a meta algorithm. It's not, you can't code it in Python or Ray or any of these systems without saying how we're going to estimate the advantage and how we're going to do the update. But supposing that you could implement it, you would get some nice guarantees. I'm not going to go through the analysis, but basically what it says is that, so this expectation is what you're trying to optimize, and if you're able to get it below 0, then you're guaranteed that your new policy is better than the old one. And that's something that you can empirically measure, so you know when you're succeeding. And sort of qualitatively, you'll succeed when you have a policy that's not the best in your class, right? You can't expect to improve it if you already have the best. If the class is rich enough that it can represent an improvement, and basically training succeeds, that you're actually able to find within your hypothesis class this policy that causes an improvement. So there are a couple of specific algorithms within this class that I wanted to point out. So one of them is called Dagger. I just wanted to point out this is not the same as the Dagger that Mike presented. I also wanted to point out I think we got the name first. So anyway, we capitalized the first 2 letters, so you can tell the difference between the algorithms. So it stands for data set aggregation. So the algorithm, the details aren't important, except that what you wind up doing is solving a classification problem on every iteration using what's called a no-regret learner. So no-regret learners are a very nice, if you're interested in machine learning theory, you should read up on them. They're kind of cool. But the key thing to know about them is that neural nets are not one of them. And so what this lets you do is, if you're willing to restrict yourself to the class of no-regret learners, this gives you a way that has some nice results you can prove about the improvement in the policy. So the other one I wanted to point out is, instead of completely solving this classification problem using a no-regret learner, it's also possible to write an algorithm that does a gradient step, much like SGD, but with a slightly different rule for you're calculating the gradient of something else. And so another catchy acronym for this one's called aggravated. Differentiable, that's the D version of aggregate values to imitate. One of my collaborators has an excessive fondness of good acronyms, as you can probably tell from the past 2 slides. Anyway, so the point here is that you don't have to restrict yourself with this newer version of the algorithm to a no-regret learner. You can do it with any differentiable learner, any learner where you can make a gradient descent update step. And so in both of these cases, what we've done is we've taken a supervised learner and we've used it to we've trained our neural network not by backpropagation through time, not as a recurrent neural network, but by reduction to a supervised learning algorithm. And empirically, this actually seems to help. The print is probably too small to see, but for example, on this this plot here, this is what you there's a baseline with random. So if you start from random initialization, you train several different algorithms, and they all get up to some level of performance. And then, for example, this green line is the vanilla version of the algorithm that I just described, and it's able. You start with a smart initialization, and you can do more gradient descent to get yourself better, and it winds up in a better local optimum. All right, so how much time do I have left? I'm done. Okay, so in that case, I think I'll stop here and just summarize and say that basically what I'm trying to do is to figure out how to take these deep networks that are so efficient, so useful in practice, and make them bolt-on semantics that's more like a graphical model. And to try and gain some benefit from doing that. Not just the benefit of interpretability, but benefits in actual practical performance as well. So thank you.
I'm going to request all our speakers to actually come up. And then if anyone in the audience has questions, please raise your hands. We have mic runners here who will get a mic to you.
All right. Where do you want us to stand?
Oh, actually, maybe there, in the spotlight.
In the spotlight, of course.
So as we're figuring this out, as to questions from the audience, maybe I can start off. I had a question about strong guarantees. So it looks like there's this trend. Finally, we've reached a point where they're programming their tools, including programming language support, that will allow us to hold programs responsible for what they're doing. Right? Strong guarantees from programs. There's always been this move, model checking and systematic testing, but now verification in terms of a proof. So you fail at the compile step as opposed to running your program. And now all of a sudden we are hit with this wave of models that can potentially replace programs that are learning from samples, and it's not clear if these samples, it's not clear how robust they are, right? So is this taking us back a step? We've just begun to take a step forward, and are we going to be taking a step back? Do you have an opinion on this?
Yeah, let me push back against software 2.0. I mean, I think it's not a replacement of software 1.0 at all. It's just a different tool. So it's a commodity. You can get a neural net to learn how to maybe recognize certain class of images and visual scenes and say there's a person in them or not. You can do that with software 2.0. In other words, gather all the data of all possible scenes and all possible people and put them into a big neural net and make it better and better over the years and ship that. Okay? But that thing has done no abstraction. It's not a predictable module for all purposes. It's just a little piece. It's like an accelerator. So I don't think of it as replacing it at all. And that said, if you have a static versus dynamic, I still think dynamic is the way to go. I mean, you're just not going to see all the things that can happen in the real world when you interface with the real world, a static program. You can prove that the thing's going to do exactly the thing you hoped it to do, but what you're hoping to do is exactly wrong. So you get a great proof that it's going to do the wrong thing. So no, I think it's all about computer scientists have got to realize that the next wave is interfacing with the real world with all of its vagaries, and not proving that what happens inside the computer is what you thought would happen.
So I think there's some really exciting work that's going on at Stanford from Dorsa, who just came over, and other folks are working on validation and verification. Sort of this, they call themselves the AI safety group, but trying to say, even if you have a black box view of what's going on underneath the covers, can you do higher level sort of proofs on it? So Michael Korkendorfer, who actually worries about planes turning left, right, and center, actually has some pretty exciting stuff where he's able to say, yes, indeed, we can verify that the plane, when it claims it's going to turn left for control 3, will turn left. So that's one issue. So there are a whole host of places where people have paid the cost for verification to build software products for a long period of time. But the trend seems to be going kind of the other way in my mind. I mean, when Python first came around, everyone said, oh, it doesn't have types, it doesn't catch anything at compile time, no one's going to use it. But the amount of stuff that's built on top of it is truly staggering, right? And so, as Mike says, and I agree, the pieces that people are building right now with these neural nets, they are kind of these individual components. But those individual components and those individual functional teams are building most of the applications that are being built at the hyperscalers. And so I think in one way where we're in agreement is we need abstractions to be able to compose those things and understand them and validate what's going on. We need some notion of modularity, but I think it's a new notion of modularity. It's not the traditional, like software 1.0 wasn't that great, right? It's not like we solved all these problems and didn't have bugs and understood what was going on. It was kind of a shit show, I think is the technical term. So, the comparison in the bar is pretty low. So I think the interesting question and where we probably are in agreement is, okay, we have these great pattern matching engines. They allow us to do certain tasks that are, just too difficult to program kind of tediously, line by line. How do we build them into realistic systems that don't fall over in the wild? And right now we have machine learning systems that are deployed that make stupid errors day in, day out, hundreds of times a day, where you can't imagine why they get that wrong. So we got to do something there. And I think Mike's right. It's probably going to be some amount of abstraction of how do we program these things. But you're no longer programming like jumps and for loops and things like that. You're programming at a much higher level of abstraction, and it's a challenge for computer science to get there.
My phone fails to autocomplete my name every time. So
yeah,
this is an example of...
Yeah, that's been one that's been on Twitter a lot recently. Yeah, really, yeah. Seems pretty simple.
Yeah.
Yeah.
So I have to agree with this idea that abstraction is going to be the really important thing, and I don't think we're there yet. I don't think we know the right way that AI systems are going to do abstraction, that you're going to be able to compose AI systems with one another. And I think this is, it's a grand frontier for research, because I think there are a bunch of really interesting ideas out there, but nobody's solved it.
Are there questions in the audience? Someone's waving at me, telling me we're out of time, but I have one more question. So this is about benchmarks. So it looks like there are a lot of algorithms, new algorithms people are coming up with, highlighting their awesomeness, including new hardware that people are coming up with. And people have begun to take the baby steps of defining benchmarks so that there can be some common substrate that you can use for comparison. So you might have heard of MLPerf, right, as being an example where they're collating a bunch of models, working models that different people can actually use as a benchmark. But that's just a first small step. Do you have thoughts on what the benchmark should look like? What's missing in there that ought to be there from like an end-to-end perspective, maybe? And not just individual algorithms like image classification.
One thing I'll plug there is Matej Zaharia and Peter Bayless did a huge amount of work on DawnBench, which came out and now is moving in to be part of the MLPerf effort. And I think they had a great vision there that I understand about trying to hold people's feet to the fire and understand how to bring back that level of sort of indirection or abstraction that allows people to optimize models independently of their applications. I think Mike made a great reference to this, and I agree. The current set of end-to-end models is kind of a disaster because you can't work on one component without affecting every other component. And so benchmarks are one way to potentially drive, like, okay, we're going to understand this level. I haven't given it as much thought as those folks. You should definitely ask Matej. I think he's giving a talk in the next session. He's thought about this a lot more deeply. But the current benchmarks are kind of just the traditional horse races, right? They're just, hey, this looks like a spec benchmark. We want to see how fast do we go. There's nothing about sample efficiency. There's nothing about data augmentation. There's just the inklings of what's going to be around mobile performance, which is a huge and massive area. That's something that's coming online. So benchmarking that's closer to what people are building is an obvious direction to go. And I think it's something, I hope that MLPerf is one of many efforts. I hope it doesn't get controlled by just corporations. And Sumit had a great tweet about exactly that point, that academics really should be playing a bigger role and kind of being neutral arbiters of, hey, here's what's interesting and exciting. And Matej and Peter deserve a lot of credit for going out there and doing a lot of unglamorous work to get that thing running. So.
So on that note, I think like benchmarks are important in terms of defining the workload, but also in terms of defining what are the metrics that people should actually be measuring. I think often there's a lot of games that can be played in terms of, let's say you're running the same net, but whether or not you batch or not batch, whether or not you're designing, how much do you rely on off-chip memory, on-chip memory, thinking more from the mobile side of things. It's really important to give a comprehensive set of metrics to validate those particular benchmarks. So not just the workload, but what are the metrics that should be evaluated as well, should also be incorporated. So yeah.
I first of all just need to emphasize again, this is not one little field. This is not databases. This is huge, huge. It's all about everything having to do with, all of A/B testing is included in here. All of control theory is included, all of natural language processing. It's just, this is massive. And so there's not going to, it can't be a few benchmarks. So with Chris, I totally agree on this.
But it looks like
it's good. There's a need for a lot of them and lots of for testing various aspects of it. But, and I agree with her too. It's all, since it is about not just what's inside the computer. It's about what's in the real world. The loss functions should be things that people care about. So they should have utilities there. They should be worried about dangers that you could get into, the situations you get. I mentioned provenance earlier. Let me just kind of bring that back out a little bit. Database people are the only ones I know about who really talk about this. But I think they have so much more they could do with it. Because provenance is that a piece of data should be tagged with where it was where it was found and what various metadata about it. In the statistical setting, the question is how relevant is it? So you're a doctor, you're trying to decide a treatment for me. Well, you look around. Is there any other people I've ever seen like this person? Right? That's provenance. And how relevant is that data I collect on that person? And that person's living over there in Africa. Is it relevant, or is it that whole collection of issues is relevant for a decision in a particular context? That's provenance, broadly writ. And so thinking about benchmarks for that, I can't, it's very hard. But it's the key part. It is a key part. It's one of 100 key parts of the problem. So yes, we got to be quantitative and all that, but let's definitely not get to a few benchmarks and have them be neural nets, applied to images too soon, because that would really kill off the bigger picture.
And one thing I should also plug in there, which is on this thing, is there's a great paper by Percy Liang and his co-authors. Percy's amazing. Is about sort of where QA systems kind of went awry, right? So there's a squad benchmark that people put out. I mean, Percy, some of my students, some of his students, he did this whole thing about squad with Pranav, and then it got kind of gamed to no end. Yeah. And so Percy being fantastic.
And click-through rate has gotten gamed, and our society is suffering from it. So definitely got to think about real metrics that matter to human beings out there.
He published a paper that's an ACL that I would advise checking out about how you can fool these systems and how they don't exhibit any of the kind of understanding, no matter, anonymous corporations putting out beating human level metrics. I won't say which one.
One, not in Seattle, I guess.
not in a rainy climate. But I think that sort of introspection only happens with a benchmark. So you could view it as negative and say, oh, poo-poo the benchmark, but actually it drove a huge amount of work and said, oh, actually the interesting challenge is over here, and forced researchers to say, hey, I thought all these features were important. They didn't show up at all in performance, but this robustness thing is really the place where we need to focus on. So I think these benchmarks are going to play an outsized role in a really empirical science going forward.
Yeah, I think that's right. I think you have to think of a benchmark not as a fixed target, but as a way to discover the next benchmark, right? Mm-hmm. As soon as you figure out how to cheat the first benchmark, that guides you in designing a second one.
Right.
So I guess we're over time. If people have questions, please continue the discussion in the break. So I think the next session starts at 3. Let's thank our speakers once again for their time.